Hello, and welcome to this episode of our science series. I'm Eric, and today we are diving deep into the structure of the atom, specifically how quantum mechanics has shaped our modern understanding of atomic theory and how it explains the pattern we see in the periodic table. To begin, let's rewind a little, back to the early ideas of the atom. The journey starts with John Dalton, who imagined atom as solid, indivisible squares, each type of an atom belonging to a different element. This model was simple but powerful for its time. Then came J.J. Thomson, who discovered the electron and proposed a new model. Atoms were no longer solid balls, but more like positively charged matter with embedded negatively charged electrons, an idea famously called the plum pudding model. However, this model didn't last long. In 1911, Ernest Rutherford's Guilfoyle experiment showed that atoms are mostly empty space, with a dense, positively charged center, the nucleus, where most of the mass is concentrated. Electrons, he suggests, orbited the nucleus like planets around the sun. But even this had problems. If electrons were truly orbiting like planets, they should spiral into the nucleus due to the electromagnetic attraction. That's where Niels Bohr comes in. He introduced the idea of energy levels, specific distance from the nucleus, where electrons could exist without losing energy. Electrons could jump between this level by absorbing or emitting energy, which helped explain atomic emission spectra. Yet, Bohr's model still couldn't fully explain the behavior of atoms with more than one electrons. That's when the quantum mechanical model emerged. Erwin Schrödinger proposed that instead of following defined orbits, electrons behave like waves, and we can only predict where an electron is likely to be. These areas of probability are called orbitals. At the same time, Werner Heisenberg introduced the uncertainty principle, stating that we can't know both the exact position and momentums of electrons at the same time. This marked shift from thinking of electrons as particles in fixed space to treating them as existing in cloud, like regions around the nucleus. With this framework in place, we can now understand how electrons are arranged in atoms. Electrons are described using a set of 4 quantum numbers. These numbers tell us the energy level, the shape of the orbital, the orientations of the orbital in space, and the direction the electron is spinning. Together, they provide a unique identity for every electron in an atom. Electrons fill up these orbitals in a specific way, starting from the lowest energy level and moving upward. They follow rules like the Pauli exclusion principle, which state that no 2 electrons in the same atom can have the exact same set of quantum numbers, and Hahm's rule, which says electrons prefer to occupy empty orbitals within a sublevel before pairing up. Now, how does this relate to the periodic table? The periodic table isn't just a list of elements, it is a map of patterns or trends that are deeply connected to atomic structure. One of the most noticeable trends is atomic radius, which refers to the size of an atom. As you move from left to right across a period, atomic radius decreases. This happens because more protons are added to the nucleus, pulling the electrons closer due to a stronger attraction. However, as you move down group, atoms get larger. This is because electrons are added to higher energy levels, farther from the nucleus. Another trend is ionization energy, the energy required to remove an electron from an atom. As we move across a period from left to right, ionization increases. The electrons are held more tightly by the increasing positive charge of the nucleus, making them harder to remove. Without a group, ionization and energy decrease because the outer electrons are farther from the nucleus and experience more shielding from inner electrons, making them easier to pull away. Electronegativity follows a similar trend. It measures how strongly an atom attracts electrons in a chemical bond. It is increased across a period and decreased down a group. Elements like fluorine and oxygen are highly electronegative because their nucleus strongly attract electrons. Electron affinities, which is the energy change when atom gains an electron, also reflect these ideas. Atoms with nearly 4 outer shells, like the halogens, tend to release energy when gaining an electron, making them more stable. On the other hand, atoms with 4 or nearly empty shells don't gain electrons as easily. All these periodic trends, atomic radius, ionization energy, electronegativities, and electron affinity, can be explained through 3 key ideas from quantum theory: effective nuclear charge, shielding, and orbital penetration. Effective nuclear charge is the net attraction felt by outer electrons after accounting for the repulsion from inner electrons. Shielding is the protection outer electrons receive from this inner electron cloud, weakening the nucleus pole. Orbital penetrations explain how some electrons, even if they are in higher energy sublevels, can be close to the nucleus than others due to the shape and orientation of their orbitals. It's fascinating to realize that behind the beautiful, organized layout of the periodic tables lies the strange and elegant world of quantum mechanics. The deeper we look into the atom, the more we see that the periodic trends we observe are not random, but the results of invisible but periodic quantum behavior. That is for today's deep dive into atomic theory and structures. From the early models of Dalton to the complex wave functions of Schrödinger, the evolutions of our understanding has been nothing short of revolutionary. And with the tool of quantum mechanics, we can now decode the hidden logic behind the elements and their behavior. Thanks for listening. I'm Eric, and I will see you next time for more exploration into the world of science.